So I'll start with an introduction, which about the origin and the production, the formation of the elements in nature, and then make a difference between stable and radioactive nuclides produced, and then go through two topics: titanium-44 and samarium-146. So the origin of the elements. To my knowledge, the first glimpse and the first understanding or start of understanding in the issue dates from 1920. It's interesting that 1920 origin of species had been understood or dealt with for decades. Origin of elements had to wait so long. And to my knowledge, again, it's first Sir Arthur Eddington, which in a lecture in the observatory, this is Greenwich Observatory. This is actually a publication. Stated that a star is drawing on some vast reservoir of energy by means unknown to us. This reservoir can scarcely be other than the subatomic energy, which it is known exists abundantly in all matter. And he continues about the possible use of that energy, which is really a vision. And in this book is the first time that one tries to understand the production of elements. Then, almost 20 years later, came this paper. This is a letter to the editor. This is what is known today as Phys-Rev letter. And in this paper, which, as you can see, is carefully in alphabetical order, these three giants of 20th century physics first understand how nuclear reactions can make elements. But then it's another 10 years, about 10 years, that the real modern what is called nuclear astrophysics comes to life with two papers. It's Al Cameron. In fact, it's not even a paper; it's a series of lectures. It was given in Purdue. The Al Cameron was done in Chalk River, and in this series of lecture, again, the modern version, the modern vision of nuclear astrophysics. Actually, this series of lectures is going to be published, republished. Re-edited next year. But this paper, which is referred to as B square FH, Burbidge, Fowler, and Hoyle, the sort of Bible of the nuclear astrophysics, and in fact, in the first figure in this paper is probably the most famous and the most well-known plot of nuclear astrophysics. It plots the abundance of the elements in the logarithmic scale versus the atomic mass, and it shows. These are measurements done by this University of Chicago school, and all the physics, all the terminology of this paper 57 is still used today. And we'll go to these few ideas now. Now this is another view of the thing. What is plotted here is the chart of nuclides. Z is on the y direction and N here. Each of these little squares is a nuclide, and the black nuclides are the stable elements. Those we are talking about right now. And what is in different frames are the different processes nature uses to create these elements. I will not. The very low side, the Big Bang, is very important, but I will not discuss it. It produces mainly helium hydrogen, helium, and lithium. I will not discuss it. The cosmic rays produces nuclides, cosmogenic nuclides. This is well known here. But I will concentrate on the real, what is called the chemical elements, the elements that we know and that are around us. The stellar burning is the first step. This is an image of the sun. Sun produces its energy by burning protons. It's usually called hydrogen burning, but I like to call it proton burning because hydrogen has nothing to do with it. And what it does, it fuses 4 protons into a helium and creates energy, and this is the energy that makes us live, or makes us... in fact, in stellar burning, what happens is that the nuclear energy which is produced, the nuclear fusion energy which is produced, sustains the weight of the weight of the planet, of the star, sorry, and prevents it from collapse. So there is this energy created against the negative gravitational energy, and the star is in equilibrium. But the thing that was not understood is that how that possibly can be, because to make a reaction like that, these 4 protons, of course, are not in one step. It's different steps which burn. But we have to make a reaction between 2 protons, which are charged particles, and they cannot really get close or make a reaction if they don't have enough energy. And they don't have enough energy. The situation is the following. I have a little cartoon here. I mean, these are the two protons which are repelled from each other. So if they get close to each other, they bounce back because they don't have the energy. And it was not understood why on Earth, on the Sun, the protons can produce energy, since they cannot even get close enough together. And this is the achievement of alpha, beta, gamma, alpha, beta, and gamma, to understand that this is really quantum mechanics. In quantum mechanics, the particles can go, and with small probability they can penetrate the repulsion and make a nuclear reaction. In this case, produce something like neutrons or something else. So this was the major step in understanding this stellar burning, because and it's in fact what happens is that the protons in the sun are with very low energies, the thermal energy. Thermal energy is 1 keV or something like that, but the height of this barrier is 600 keV. So how possibly? I mean, this is like going through this wall. This is literally like going through this wall, and this still can happen with a very low probability, which can be calculated. And this what makes the sun burn, create energy, and sustain itself, and it goes slow because the probability is low. But eventually, in a star, and now I'm talking about more massive star than the sun, they eventually will happen also to the sun. Eventually, in a few billion years, the protons are run out. And what remains are the ashes of this burning. This is really a burning. Burning is an exothermal reaction. So it's an exothermal reaction to produce something. And what is left is helium-4, then the star collapses, and starts burning the ashes. The ashes, in a good furnace, you also burn the ashes, right? Because you don't want to waste energy. So this is what the star is doing. And this is an example of such a star. This is it's called Betelgeuse. It's a huge star. You can see the size of the star, and this is something which I understood. In the core of this star, the helium is burning and producing heavier elements. And the outer shell, the huge outer shell, the size of the outer shell is larger than the solar system. And it's likely to happen to the sun, not in our lifetime, but at the end of the sun's lifetime. So this is part of the constellation Orion, which is known. One sees it, I think, also in the southern hemisphere. This is this star here, which is it's one of the big stars, and it's red. So it's called a red giant, because it's huge and because it's red. So this burning of helium now, the same principle. By a higher temperature, the burning of helium produced with a sort of coincidental or one of these fluke of nature, it can produce carbon-12. I'm not going to enter that, but this is amazing that it does that. Also, not in one step, but in two steps this time. Produces carbon, and then will go like that up to a certain point. But what is important is that this is the stage where also heavier elements are produced. Heavier elements cannot be produced in part because of this repulsion. Repulsion gets bigger and bigger, and the only way to produce heavy elements that we know, not the iron, but above the iron, we know there's gold, uranium, who knows. These elements are produced by neutron captures, and this is a scheme of the thing starting from iron. Now, where comes the iron from? Iron comes from a previous generation, which is in that star. That star has some seeds of a previous generation, and by capturing neutrons, it can climb up the chart of nuclides. This is the so-called S process, the slow process, where it captures one neutron, and then another neutron, and then, for example, here another. Then the capture rate is slow, so it decays, goes back to stability, and so on, and climbs and goes practically until bismuth 209. Cannot jump bismuth 209. So there is another process that we will go through shortly. But this is the synthesis of the heavy elements, and this occurs again in this star, because it can produce enough neutrons for that. But the star itself is still burning its helium, and will eventually burn more and more. But all this stellar burning has an end, because there's a point where fusion cannot create energy. So the star can then not sustain itself. And this is for massive star. By the time that it has reached this point, it has created all the elements up to iron. Iron, the most stable elements. I mean, the most with the most binding energy per nucleon. So it produces energy to fuse, and then the star looks. Of course, it's an ideal scale. Image, but the star looks like that, and then if it's a big star, it will collapse into a supernova. This is an example of a supernova here. This one here, and this is a galaxy. You can see that the energy of the supernova outshines practically the whole galaxy. It's a huge amount of that, 10 to the 51 ergs. Now I have a movie here which doesn't work, so I apologize. So all the origin of the elements is a sort of cycle, where we start with burning, first creating the sun, or the sun-like star, which burns the hydrogen and burns something more, helium, and then here at this stage burns helium, and eventually, if it's a massive star, and this is how some of the heavy elements are produced and dispersed back to space, leaving behind either a neutron star or black hole. But this material which has dispersed eventually recollapse, forms a new generation of stars. So this is how we understand that the galaxy gets enriched in chemical elements So the first stars were very metal poor, which means very poor in heavy elements. But they very quickly started forming galaxies like ours and stars like our sun, which has the variety of elements that we know. In fact, this is another view of the abundance of elements. This is the solar system. This is the distribution of elements. As you can see, there's mostly hydrogen and helium. This is what is in the sun, and the rest is here. And this is actually, this is interesting. We have a good knowledge of that because it's our solar system. But it's representative of the whole Milky Way, which is by itself is interesting. It's very close to that. I mean, there are some differences, but it's very different from what we know in the Earth's crust because all sorts of geochemical and biological phenomena, and it's very different from our body, even. So these two things are very different. But as far as physics is concerned, the elements of our solar system seem to be a robust distribution. It's like that in the galaxy, and apparently not far, as far as we know, also in other galaxies. So this is another view of the more detailed. I mean, the distribution of elements here is plotted against atomic number, not atomic mass, like in the first plot. So it looks a little different. This is the abundance normalized. Traditionally, in this case, these are this compilation. But there are since Suess and Urey, which I showed before and was used by B²FH, there have been many iterations on that. And this is known from photometry of the sun, the abundance of the elements, and also of meteorites. Some of the meteorites are pristine pieces of solar system. So this is all the data here. Of course, these are all data. Come from these two sources, which show the abundance of elements in the solar system. Now, these are stable elements. We're talking about stable elements, which we have here. And we have to realize that stable elements, once it's produced in a star, it could have been produced in any star of the galaxy, and eventually ended up in the solar system, ended up on Earth, ended up in our body. For every one of our oxygen atoms could have been produced in a star. And once it was produced, it stays, because there's nowhere to go. And some minute part is destroyed, but once it's produced, it's there, and evolves, and so on. So this is stable elements. So many of these atoms could have been produced. Who knows where in the galaxy, and who knows when. But there is a family of elements, of nuclides, rather, which are not stable. This family has this particularity that they are not stable, so they have a half-life, but their half-life is long enough to have survived, to some extent, the galaxy and the travel, and the creation, the travel, and eventually these elements have ended up in what is called the early solar system. The early solar system is the solar system just at formation, when this cloud, which I showed before, started to collapse in a new star, in a new system. And they, each one has a different half-life. So they are capable to say more than stable elements. Stable elements don't say anything about the time, because once they could have been created at the origin of the universe, so very close to it. These must, if they exist in the early solar system, they must have been produced not more than a few half-lives before. So each one has something to say about the history about time, evolution, which is different from stable elements. And the other thing which is interesting in these elements, for us experimentalists, and these nuclides are all the AMS nuclides, the nuclides which are detected with this exquisite sensitivity with AMS, with accelerator mass spectrometry. This is not a miracle that this is the same, because they have this kind of half-lives which make them useful for dating, for whatever, and measurable with AMS. So this is a bizarre coincidence, which is not a coincidence, but it's a bizarre association. And this is what attracted me, among others, into connecting between the two fields. Aluminum-26 is known to many here. It was in the early solar system. By the way, the early solar system is known because we measure in meteorites. What is plotted here is anomalies, isotopic anomalies of the daughter as plotted against aluminum. And this correlation, what is shown here is that in fact from an initial value, the amount of magnesium which is added is proportional to aluminum. So this magnesium-26, which is a daughter of aluminum, comes from aluminum-26, and it gives the initial abundance of aluminum-26. And in the last years, which in the last decade, what has been measured now is that not only it was in the early solar system, but it's now live in the galaxy. One measures in the galaxy. This is a plot of the intensity of photons emitted by this radioactivity, and these are photons which we can measure in the lab. This is the intensity of photons of that energy, this gamma ray, so transition in the decay of aluminum-26, and this is measured now, identified in the galaxy, which means that aluminum-26 is live in the galaxy. So it's live in the galaxy, it's produced. It's produced continuously, and with this kind of half-life, it's a sort of measure of the nucleosynthesis activity along time, along the recent million years. I'm going to now to sum up two examples of how AMS can contribute to that field in two examples, and one is titanium-44, which is known, it was known even before, as a supernova signature. It's one of these elements in the chain of alpha reactions between helium and iron. And this is known. It's not in this plot here because it was not in the early solar system. It's too short-lived. It didn't make it to the early solar system. But in fact, it was seen also as a live radioactivity. This is the Cassiopeia A constellation in the northern hemisphere, and somewhere in this constellation there's a point which is not visible the naked eye. But this point is a remnant of a supernova. In fact, this is the last known supernova of our galaxy. It may have been spotted. It's not clear in 1680, but that's a supernova which exploded in our galaxy, as opposed to 1987A and other galaxies which I showed with our other galaxies. And what is a lot is known about this remnant. This is the remnant seen in all sorts of wavelengths: radio, infrared, visible, X. But it's the amazing thing is that not only is it seen as all these wavelengths, but it's seen also as radioactivity, the titanium-44 specific activity. And this is shown here. This is also a map of, it's like the aluminum-26 before, but it's a very small spot in the sky in galactic longitude and latitude. So this spot here, which is a flux of photons of that energy, again, photons which comes from the decay of the radioactive titanium-44, 60 years half-life. And this is the place of the remnant seen in other. So it's identified from this remnant, from this Cassiopeia A, and this supernova remnant. And since one knows a lot of things, one can calculate from this flux how much titanium 44 was produced. And in fact, what is interesting and not yet solved or not yet understood is that this flux that one measures is much larger by a factor of 10 than what should be if we understand a supernova right. Supernova is very complicated, so it's not clear that we understand it right. But what we measure in this case is larger. So the production of titanium-44, and now it's a kind of nuclear astrophysics, the way the titanium-44 is here. See, the half-life is wrong because it's wrong. And it's produced basically by alpha capture on calcium-40. And some of it, of course, decays back, but some remains. And what remains is what we see. We see with the gamma spectrometer, the gamma astronomy spectrometers. And we decided to do that in the lab, to do our little nuclear synthesis in the lab. I mean, this, of course, one does with a nuclear reaction. But so the experiment was the following. To have a helium gas target, for different reasons, we do the reaction with a helium gas target, and a calcium-40 beam. So some of these reaction occurs, and the recoil is implanted in a catcher, and then once it's implanted in a catcher, one can extract it chemically and count with AMS. And this will measure, I mean, the idea was to see whether there is in this production cross-section, the production probability, something which explains why it's so large in this Cassiopeia A. So I'm not going to, this is actually the supernova, the lab supernova. This is the calcium beam in a helium gas. This is the catcher here. One can guess it there. And so this is how the experiment was done. And again, the titanium-44 gets implanted in this catcher, gets etched and measured by AMS. I'm not going to go through the AMS measurements because it's very, I mean, you could do this here every day, the AMS measurement itself. And but what we found is indeed there's a higher cross section than what was known. I mean, there are more resonances and more yield in this production that was known before, known experimentally before. And we found a little more production. This is the rate of the reaction. This is kind of astrophysical unit. As a function of temperature, I mean, again, in the star, it's not an accelerator. In the star, what makes the reaction possible is the temperature of the star. And this is, of course, for such, I mean, relatively heavy calcium and alpha reactants, the temperature has to be high. It's not in the range of 10 to the 9. And we indeed find a larger production, but not enough to produce. But it's a piece of information which AMS sort of bridges into the field. The second topic concerns Samarium 146. Samarium 146 is one of these again early solar radioactivities known to have been there in the solar system. But let me just present the nuclide in its vicinity in the table of nuclides. This is again the table of nuclides in more details. The black are stable. The blue squares are stable isotopes which can be produced by the S process. Remember, S process is this slow capture process in which neutrons are captured one by one, if you want, and produce elements. Many of the elements here, but some of them cannot be produced because, for example, this one, the thing has decayed before it could absorb another neutron. So this cannot be produced by the slow process. It is produced by what is called the rapid process. Rapid process is a process where, and it likely occurs in supernova, but it's not known really where. but sites where the flux of neutron is huge, and as soon as it occurs, the yield is brought to the many captures of neutrons. Many neutrons are captured and eventually decay to this neutron rich from there, from somewhere very far away, decay to these nuclides. So this is the R process. And there is one among the stable nuclides which cannot be produced either by the S or the R, because it's proton rich, and there's no way it can be produced. So it's called the P process. It's a proton. P comes from nucleus, this photonucleon. It must have to do with photo dissociation. For example, gamma n can produce this and this and this, gamma n, or P gamma, and so on. But this is a strange and unlikely process, but it's a fact that it's there. I mean, samarium it's a 3%, it's not a rare, it's a stable nuclide. So it's there. It's there, I mean, it's stable probably because this is the n equal 82 neutron line, and this gives stability to these nuclei. But anyway, it's there. Another case is our samarium 146, which is also a P process, which is also, I mentioned P process here, but it's also a P process because it cannot be produced by neutron captures alone. It cannot. There's no neutron captures which brings you to here, except several neutron captures, which is unlikely. Now, what is interesting is that samarium 146 decay by alpha. I mean, it's not anymore in the solar system. It has decayed, has extinct. It was in the early solar system, as I said, but this alpha decay with a half-life of 100 million years gives a handle on chronology, on chronometry, on this scale. There are not many cases where one does chronometry on the 100, or dating in the 100 mega-year scale. This is one. And in fact, very early it was proposed as such, even before it was known that it had been in the early solar system. So the samarium 146, again, this is one of these plots which geochemists love. This is called 3-isotope plots. It's one isotope, second isotope, and third isotope. So again, it's a correlation between the daughter of 146, samarium, the alpha daughter, and this is this guy, and samarium 146. And this correlation shows that it was there in the early solar system. And so the scenario of these early solar activities is not true only for samarium, but this is the general scenario, is that, again, this is the early solar system, but it was formed out of the interstellar medium, which collects all the debris from supernovae and all other stars which disperse the elements in space. So there are all sorts of sources which produces, for example, in a uniform way, but this is a simplification, it produces nuclides. At some point, the cloud forms, which eventually will collapse in the star, or the sun, in our case, in this case, and also planet around. And it takes some time. I mean, so if you assume, for example, that for nuclides such as samarium, this steady state contains a steady state abundance of samarium 146 or other nuclides, but in this case, it will decay from some time with this decay between the steady state and what is left in the early solar system. And so this is what it was meant by Schramm, Odus and Schramm, that it gives a chronometry of that situation. But even more interesting, more interesting, but as interesting at least, is the fact that samarium-146 and also the other isotope here, so samarium-147 has a half-life, an alpha half-life of 10 to the 11 years. Very long half-life. And both these alpha decays, and these are geochronometers. I will not discuss this. This is one of these dating tools for the age of the galaxy, in fact, of the solar system. This decay. But this is too short to measure the solar system itself because it's extinct now. But this decay has got in the really very recent years, the last 5 years, or maybe more. I mean, it started in 2005. It was discovered something interesting. It's discovered that Earth, the terrestrial rocks, have a different 142 abundance, the daughter of 146, a different abundance than chondrite meteorites. Chondrite meteorites are the solar system, and it is believed that the Earth is chondritic, basically, apart from the differentiation that has occurred. But the fact that the 142 is enriched compared to chondrites means that a differentiation must have occurred while 146 was still live. And this, of course, gives a chronology, and depends. And all these, also the early solar system, and this chronology depends on the half-life, and that's why we embarked in a measurement of the half-life, which we have now concluded. Very surprisingly, with a different number that was known before. The half-life had been measured 4 times, every 20 years about, and first by Glenn Seaborg and collaborators. And as you can see, those 2 values were low, but then there were surprisingly 2 measurements, also 20 years apart, which gave the same value and same uncertainty. So when the values are discordant, you want to measure them again. But in this case, they are not discordant, so you also want them to measure again. So we measured them again, and we did it a little differently than before. I don't say better, but I say differently. And the method is the following. This is the decay of samarium-46. This is the decay of 147. And what we measure is the ratio of the 2 activities. The activity of 146 is given by this expression. This is the activity is the number of atoms. This is the half-life, which we want to measure. This is the same one for 147. And if you make the ratio, this half-life here can be expressed as the half-life of 147, which is well known. Less than 1% uncertainty, this is how it's known. And the relation between the 2 is the atom number, atom ratio, and inverse activity ratio. So if one measures the activity ratio and the number of atoms, not the number of atoms, the ratio, the atom ratio, one has a value. And the fact these are ratios are much better than, I mean, measure ratio is always better than measure in absolute numbers, and this is why we did it this way. And this required in our mind accelerator mass spectrometry. Now you can argue if we did this because we want to do accelerator mass spectrometry or the opposite, but the fact is it doesn't matter. The result is that there is a measurement, and this was done by AMS because, as usual, the isobaric separation is necessary. I mean, if this is you have to produce it. And once you produce it, you have to separate it from chemical impurities. And so the production, we did it three independent ways. A fast neutron production always starting from 147, N to N. Gamma N, a Bremsstrahlung, gamma N. This is actually a P process way to do it. Yeah? And another way, P to N, this is a cyclotron, P to N, and then this short-lived thing decays here. So we have a material which is has both 146 and 147. We measure the activity ratio, and we measure the atom ratio. A few words, since I'm a little late, about this was done at Argonne. It's a different accelerator mass spectrometry. The reason that it has to be different is the high energy that one needs to separate isobars as heavy as samarium and neodymium. So this was done with an accelerator which can boost the energy to several MeV per nucleon for such heavy nuclides, starting with positive ions which are highly charged. This is here. This is the sample. Here you can see on the side, and this is how it's done. Putting in the ECR chamber. This is and by the way, we are now in the process of improving all that by sample changer. I mean, this is an enlarged version of the sample changers that are known in AMS in general. It pushes the sample to the ECR, and also laser ablation. Laser ablation I will not come into. It's a way to feed the ion source with material. The isobaric separation is done with a gas-filled magnet, something also that you're familiar with here because you're building one. And the gas-filled magnet, what it does is disperse elements, like even if they have the same number, mass number, they disperse elements, and then one can separate them. And these are spectra of the alpha activity. So these are the alpha energy is low. This is one of the problems. So here we measure only the ratio between the samarium and 47. So these are the three samples, gamma, N, and proton activated, and each of them one can determine a ratio, 146 to 147. And the mass spectrometry here, again, this is the separation and identification of the 146 samarium, this blob there, which one can count. And the results are shown here. Again, as I said, the result surprised us, but we got to the conclusion that if we measured it, we have to publish it. And the result is that for many samples, produced in a dependent way, gamma, neutron, or proton activated. And what is plotted here is the ratio of the measured half-life to the adopted half-life, that is value 103 plus minus 5. And the ratio, as you can see, is not 1, but is 0.66, consistently for many different samples. And these are even averages of many measurements for each sample. So in our mind, it shows that the half-life is shorter, significantly shorter. 68 is the value that we attribute. And this, of course, has implication on the chronology. I think I am out of time, but it has implication on the chronology. What it does, this shorter half-life, squeezes the chronology. It makes things happen faster, because for given abundances, things had to happen faster, even faster than was in some case. This is an example of rocks which were dated. This is a so-called isochron of rocks which were formed about 290 million years, as early. The sedimentary rocks. These are probably the oldest rocks known on Earth. Rocks, not. And now we come to the conclusion that they were even older than that, by something like close to 100 million years, with this new half-life. And same thing on the moon, on lunar rocks. So this is a reinterpretation of these isochrons, of course. But what is an indication that maybe it's right is this lunar rock. This is a lunar rock brought by Apollo 16, So this is a mineral which have been dated by different techniques. Some of them very precise, lead. Another one samarium 147, the one which I showed before. And these are 2 sigma error bars, and this didn't fit. While now with our values, it doesn't fit either, but it at least overlaps the 2 sigmas. And which is interesting, this age here, or this age after solar system, is very similar to that of this isochrone here. This isochrone here is now reduced to 180, and so it may imply that there was a major rock formation event on the moon, which is now consistently dated. All right, so this is what I wanted to say. I mean, so 2 examples of AMS entering these disciplines, these research in nuclear astrophysics and in geochemistry. Geochemistry is, I don't know why chemistry is physics. Everything is physics, and this is my collaboration. Noi Kinoshita was a postdoc at Tsukuba. Was before in Kanazawa University, a graduate student, and mainly the large argon group, without which the AMS could not have been done, simply could not have been done. I think this is the example. This is the measurement of an isobaric separation, a quantitative separation, which is the heaviest done so far. So I like to end up with this philosophical statement. I don't know if it's that deep, but I think AMS is one of these tools which not only serves science but drives science. And this, I think, has been true all along the history of AMS. It has not only followed science, but it has created science. And I'm sure that it will do so for time to come. Thank you.